Hello and welcome to Week 11, Part 4 of EGM310, Image Decomposition and Transformation. In this lesson, we will learn about the ways that we can transform our image data to help with interpretation and visualization. In the last lesson, we learned about how we can visually interpret images in order to identify the objects in them. We've also spent some time talking about false color composites, where we combine different bands to highlight different objects to make them easier to identify. But RGB images, or even grayscale images, are not the only tools that we have at our disposal. For instance, you might know that RGB is only one example of a color system. It's far from the only one. You may remember learning about the primary colors in school: red, yellow, and blue. Most printers use cyan, yellow, magenta, and black, or CYMK, to represent color. We also have something called intensity, hue, and saturation. This is common for a lot of digital art and computer graphics, and it can be especially useful for remote sensing. In addition to transforming images into different color systems, we can also manipulate images to exploit spectral reflectance patterns or to try to maximize the differences between different bands. Intensity, hue, and saturation, or IHS, is also known as hue, saturation, and lightness. Rather than choosing red, green, and blue components, it breaks down a color value as follows. The hue component is the dominant wavelength, or what we might recognize as the color of the pixel. It's usually given as a value from 0 to 360 degrees. As you can see, the color changes as we move around this color wheel. Saturation refers to how much white is mixed in with the color. As we move out from the center of the color wheel, we decrease the saturation. Finally, we have intensity or lightness. This is how bright the pixel appears, ranging from 0, which means totally dark or black, and 1 or 100, representing totally light or white. One application that we can use for the IHS transformation is something called IHS Fusion. With this, we use high-resolution panchromatic data to sharpen or increase the resolution of the multispectral data. This is what was used to increase the apparent resolution of the image that you use for Practical 2, to take the 30-meter Landsat multispectral data and resample it to 15 meters. The way that we proceed is as follows. First, we resample the multispectral data to the same spatial resolution as the panchromatic data. This doesn't actually increase the spatial resolution, it just changes the pixel size. Next, we transform the multispectral RGB image to IHS. We have the intensity component shown here. After that, we swap out the low-resolution intensity component for the high-resolution panchromatic image. And finally, we transform the swapped IHS image back to the RGB. You can see here how the RGB image appears much sharper. We can see a lot more detail in this image than we can in this one. And this is because a lot of the detail that we see actually comes from the variation in brightness, while we can make do with less detail for color. One thing that you might notice looking at this graph is that a lot of neighboring bands are correlated. That is, many surfaces or objects have similar reflectances in nearby wavelengths. This means that we often have a lot of redundant information stored in different bands. This can make distinguishing different surfaces more difficult, as they will tend to look similar. For example, snow and clouds look quite similar in a number of different wavelengths. Distinguishing between different kinds of vegetation can be quite hard, as color differences can be very subtle. To try and get around this, we have some techniques that we can use to help maximize the differences between bands, which makes it easier to extract information from an image. An example of how we can do this is shown here. I've included an image with two different Landsat bands, the visible blue band up here on the top and the visible green band here on the bottom. The plot here shows a scatter plot of the pixel values for each band. The value in the green band is along the x-axis, and the value in the blue band is along the y-axis. And you can see that most of the values, most of the pixels, fall pretty close to this 1-to-1 line here. What this means is most of the variation, that is the actual useful information in the image, depends on how far along this line we are. We're not necessarily gaining any extra information by using both of these bands. The principal component transformation looks to take advantage of this fact. We start by essentially finding the line that best fits the data. Again, we're basically boiling down the most important information in the image, which we call the first principal component. After that, we can calculate the second principal component perpendicular to this line. And we might want to shift the axes slightly so that the minimum value along the second principal component is 0. Because of the way that we've constructed this, these two new bands, the first principal component and the second principal component, are completely uncorrelated. We've completely maximized the differences between the two bands, so we also don't have any redundancy contained within the image. This is a little bit of a toy example. We normally are doing this with all of the bands of a multispectral image, but doing this with 6 or 7 bands is very difficult to visualize on a computer screen. When we do a principal component transformation or decomposition on our original image, this is the result. For Landsat data, as I'm using here, the first principal component, PC1, consists mostly of information from the near and shortwave infrared bands. This is where the most variation occurs in the original image. PC2 consists mostly of information from the visible bands. You can especially see this because water in the principal component appears significantly brighter than in the rest of the image. And in the near infrared and shortwave infrared, water is completely black. PC3 comes mostly from the near infrared. You can see this because the vegetation looks a little bit brighter than the water. As we go further down the principal components, we're getting less and less variation. We have less and less information contained within the images. Most of the variance in the original 6-band image is contained within the first 3 or 4 principal components. And after that, we're adding less new information. We can combine the first 3 principal components to create something called a decorrelation stretch, shown here on the right. The image on the left is the true color composite. The decorrelation stretch is a way to increase the distribution of color within an image while preserving the relative characteristics of the original image. And what we can see here is most of these vegetation surfaces are a bright magenta color, indicating that their highest values are in principal component 1. Water is a bright green color, indicating that water surfaces have a significantly higher value in the second principal component than in the first or the third principal component. Most of the rest of the image appears to be different shades of red or orange or green, with some regions of very dark blue. I'll post larger versions of these images on Blackboard, and if you like, you can have a look at them and see if you can't figure out what they might represent. In addition to different kinds of transformations, we can also use bands algebraically. We can add them together, subtract them, multiply them, or divide them. These operations can all enhance the differences between different bands, helping us to identify surfaces or convey other information more easily than by using the reflectance values on their own. For example, we know that for healthy chlorophyll-producing plants, the reflection in the near infrared is significantly higher than it is in the visible red. You might notice that for most other surfaces, the reflectance in the near infrared and visible red is quite similar, or it even drops. For water or weathered basalt, it's nearly the same. For concrete, it's perhaps a slight increase. For snow, it's a very clear decrease. So if we were to look at the difference between the near infrared and red bands, we might expect that vegetation will have strongly positive values, while most of the other surfaces will have slightly positive values or even negative values. But the details might change depending on the illumination in the scene. To help counteract this, we can do something called normalizing the data. That is, we divide by the total reflectance in the two bands, which helps ensure that the comparison is determined using the illumination in the scene, that it doesn't depend on how much illumination we have. This leads us to an extremely common method for studying the health of vegetation, or to help identify vegetation, which is known as the Normalized Difference Vegetation Index, or NDVI. The NDVI is calculated as follows. We subtract the red band from the near-infrared band, then divide by the sum of the two bands. This is where the normalized component comes in. The NDVI then consists of values that fall between -1 and +1. Values much greater than 0 typically indicate healthy chlorophyll-producing vegetation, while values less than 0 typically indicate something else, either distressed vegetation or some other surface like clouds, snow and ice, or soils. We can use the NDVI to help map healthy vegetation or to help derive other information about vegetation, such as the area within a given pixel that is represented by plant leaves, or the chlorophyll concentration within leaves. I've shown an example of this here. We have values ranging from, saturating at -0.5 and +0.5. So most of the values are falling between about 0.4 and -0.4 that you can see here. And you can see that in areas where we remember seeing a lot of healthier vegetation, especially in agricultural fields, we have darker green values ranging to lighter green values, and things like water and clouds are negative. Similar to the NDVI for vegetation, we can calculate a normalized difference index for water. The NDWI makes use of the fact that for water, the reflectance in visible green wavelengths is much higher than in the near-infrared. Thus, we calculate the NDWI by subtracting the near-infrared band from the green band and dividing by their sum. The NDWI is used for, as you might have guessed, automatically mapping water bodies. We can also use it for flood detection and mapping in images, especially if we have an image from before a flood event. Large changes in NDWI are most likely indicating the presence of water. An alternative version of the NDWI, also called the NDWI very helpfully, uses the near-infrared and shortwave infrared bands. This version is used to estimate the water content in plant leaves, as the reflectance in the shortwave infrared is more heavily affected by water content than it is in the near-infrared. In this lesson, we have learned that by transforming image data, we can make more use of the information contained in the image. For example, we can use it to sharpen multispectral images by first transforming the image into intensity, hue, and saturation color space. We can also use these techniques to improve the spectral differences between different surface types and remove redundant information from bands that are close together. By using arithmetic operations, we can enhance differences in spectral reflectances between different surfaces, helping us to better identify them. Once again, you can read more about the concepts we've covered in this lesson in the textbooks, Chapter 7 of Lillis and Kiefer and Chipman, and Chapter 11 of Campbell and Wynne. You can also read more about some of these topics in the remote sensing tutorials from Natural Resources Canada. For more information about the HSL or IHS color space, I've included a link to a video from Khan Academy, and I've also included a link to a video about working with NDVI in ArcMap. That's all for this lesson. I hope you found it interesting, and if you have any questions, please don't hesitate to email me or post in the discussion forum on Blackboard. Bye!